Hello everyone. Welcome to the discussion session on tutorial number 4 of CV481. On this video, we'll cover a brief overview on the possible questions that is there on tutorial session number 4 on earth pressure, wall design, and excavations. Retaining structures such as retaining wall, basement walls, bulkheads commonly are encountered in foundation engineering as they support slopes of earth masses. Proper design and construction of these structures requires a thorough knowledge of the lateral forces that act between the retaining structures and the soil masses being retained. These lateral forces are caused by lateral earth pressure. The magnitude and distribution of lateral earth pressure depends on many factors, such as shear strength parameters of the soil being retained, the inclination of the surface of the backfill, the height and inclination of the retaining wall at the backfill interface, the nature of the wall movement under lateral earth pressure, and the adhesion and friction angle at the wall backfill interface. Some of the sample practical situation that relates earth pressure can be stated as excavations, supported sheet piles. You can see here, this is the original ground surface, and if you want to make an underground parking or basement for a high-rise multi-story building, we need to retain the soils that uh, during the excavation. These are generally supported by sheet piles. Also, if there is a mountain slope and we want to make a road on this, going one side to the other, we need to retain the soils of the slope. These are also done by roadside sheet pile walls. Crypt walls are also popular on mountain slopes. These are basically made of concrete but has perforations or slits inside so that the water can easily transmit. Concrete walls are also seen on the nearby roadside structure to also sustain the slopes of the mountains. Types of retaining wall. Generally, they are of three types. A rigid retaining wall, such as gravity retaining wall, semi-gravity walls, cantilever retaining walls, or counterfort retaining walls. If you want to show it figuratively, this is a gravity retaining wall made of plain concrete or stone masonry. This is a very traditional and conventional form of retaining wall that depends mainly on its own weight. If for a modification of this gravity retaining wall, reinforcements were allowed, this helps in reducing the size of the retaining wall. Also, as a modification of the semi-gravity retaining wall, later came the cantilever wall with much more reinforcements. This is an example of counterfort wall. As you can see, it's very similar to this cantilever retaining wall, like if we compare this portion of this section, but it has thin concrete vertical concrete slabs known as counterforts, like you see here, counterforts that tie the wall and the base slab together. Flexible retaining walls. These are very long, slender members of either steel, sheet piles, concrete, or wood. Relies on passive soil resistance and anchors for stability, often used in waterfront structures and temporary excavations. This is a figurative representation of a flexible retaining wall. On number A, we set it as a cantilever wall. If this is the slope that wants to be retained, the upslope, and when to retain the slope. And if it's a road like this, like the way we saw in the previous figure on the sample practical situations, we can put a cantilever retaining wall. As a much more low soil upslope load, to take the higher amount of extra loads of the soil, there is a modification. There is another form of literally flexible wall. These are called anchored or tieback walls. These tiebacks are generally made of steel rods that connects to an anchor of concrete blocks at the top. This helps in reducing the dimension of this cantilever retaining wall or sheet pile to a considerable distance. The third form is the mechanically stabilized earth wall. It's a form of flexible wall that have a granular backfill, geogrids or geotextile wraparound walls, gabion walls, concrete panel face walls, or metallic strip walls. In the figure, you can see this is a gabion wall. Gabion blocks of meshes, wire meshes filled with stones. We can put one over the other and thereby it can form into a wall. The joints we can put geogrids. Secondly, you can also make a wall like this geogrid or geotextile wraparound wall, the figures shown here. And we can put a wraparound rows on it and thereby, like a ladder, we can form a wall. These are metallic strip walls. Like one metallic strip, we can put one over the other and thin strips going down the backfill, and thereby this will act as a wall. The fourth one is a concrete panel face wall. These are panels topped one over the other with connected geogrids and pin connections with the geogrids that will also act as walls. Mode of failure in rigid structure. There are generally four modes of failure for rigid structures. One is the sliding. Like if this is the original position of the wall, if it slides to the right, then we call it a sliding or translational failure. If the soil at the bottom cannot retain this wall, there will be some rotations. And also the nearby soil will have bearing capacity fail. Also, if it happens that we have a failure, if this soil does not have adequate does the soil beneath it does not have adequate strength capacity. Likewise, in foundations, we could also have a shallow surface forming up. We call it a deep-seated failure. The fourth one, there could be structural cracks due to inadequate reinforcement or structural inaccuracies that we call structural failure of the retaining wall. Flexible structures, however, have five modes of failure. It could have a deep-seated failure, like the one previously explained for rigid walls. Could have rotations. It could have rotations near the base, failure of the anchor prop, and failure by bending. At rest, active, and passive earth pressure. These are the three forms of active pressure, earth pressures that depends upon the movement experienced by the vertical one on which the pressure is acting. The first case, the rest condition, are generally expressed over K subscript naught, which is the ratio of the horizontal effective stress divided by the vertical effective stress. the horizontal effective stress versus the vertical effective stress. The condition for this is that where wall movement is zero or minimal. The ideal condition of wall, but seldom achieved in reality. Second one is an active condition, which is expressed by K with a subscript A, is the relationship between the horizontal effective stress by the vertical effective stress, but it is represented when it is active, represent the horizontal stress by sigma A prime. Conditions where wall moves away from the backfill, the lowest state of lateral pressure. Case 3 is a passive condition where we have in place of sigma H prime, we have sigma P prime. This is a condition where the wall moves towards the backfill. So important thing to notice is that in active condition, the wall is moved away from the backfill, and in the passive, it is moving towards the backfill. Passive condition will give us the highest state of lateral earth pressure. Let's see on the figure. If it is a soil block, and this is a retaining wall AB, soil block adjacent to this retaining wall will be at rest position if it does not have any movement. If the wall moves away from the backfill, then this horizontal stress will be active stress or active earth pressure. This is the failure surface for the active pressure. If the wall is moving towards the backfill, it will be passive pressure. At rest earth pressure, the figure, just what we explained, you see the relationship between the vertical stress and the horizontal stress was K naught over sigma H over sigma naught. So if I have to calculate the sigma H prime, it will be K naught gamma Z. Generally, for coarse grained soil, it is the relationship is K naught 1 minus sine phi prime, where this is the effective friction angle. Above equation is good for loose backfill sand. However, for dense compacted sand backfill, it is recommended to use 1 minus sine phi times gamma d over gamma d mean minus 1 to the power 5.5. However, for clay, for overconsolidated clay, the K naught over consolidated is equals to K naught normally consolidated soil times the over consolidation ratio. Active earth pressure. As we said that in active earth pressure, the wall moves away from the soil. So if this is the initial state of stress, that is when the wall doesn't have movement, that is at rest, we not had, this is the Mohr circle, then the sigma naught and the sigma h relationship should be like this. We tell this one as a K naught state. Eventually, when the wall starts to move away from the soil, the circle, the horizontal stress will be decreasing. Thereby, it is going to go like this, and at a certain stage, it will reach the failure. That is we are attaining as active earth pressure, sigma A prime. Hence, for this particular failure envelope, if you want to see and visualize the failure plane angle, this angle is 45 degree plus 5 prime over 2. That's why the K relationship for the sigma A prime over sigma naught prime stands at 10 square 45 degree minus 5 prime over 2. On the other hand, for the passive earth pressure, this is the initial stress, just what we said previously for the active pressure. If the wall starts to move towards the backfill, this circle is going to increase. the sigma h will increase, and one stage it will reach the failure circle or the failure envelope, and that stage we are saying it is a passive earth pressure. So for this one, when we draw the failure line, we say the angle is 45 degree minus 5 prime over 2. So the KB stands for 10 square 45 degree plus 5 prime over 2. If we want to see the variation of the magnitude of lateral earth pressure with wall tilt, then it's basically like this. This is the earth pressure distribution. When it is at the zero, earth pressure, where there is no wall tilt, this is the at rest earth pressure. When it is going down, this is the active pressure, and when it is going up, wall is moving towards the soil, then it's the passive earth pressure. These are the typical values, recommended values for delta LA over delta H, delta LP over H for different types of soil. So now on the tutorial outline of the tutorial 4, there will be discussions on question number 1, that is calculation of earth pressure. Question number 2, gabion retaining wall design. Question number 3, concrete caisson design. Question number 4, excavation supported sheet pile walls. Question 5, excavation supported brace sheet pile wall design. Question 6, excavation supported H pile wall design. Thank you so much.